Hi everyone. I wanted to make a short video on the topic of weight versus mass. This topic is super important and confusing, and it's really important you understand the difference if you're going to, be at all motivated by any of the calculations you do about either of these quantities. The first thing about weight versus mass, first of all, before I move along, there is a formula for the force of gravity that you might be familiar with, where the force is equal to big G times m1 times m2 divided by r squared. This is more appropriate for for weight forces in general. I'm going to ignore this and focus on the simpler, not quite complete version of that equation, which is just that the weight force is equal to mass times the acceleration due to gravity, just for the record. So for this class, this is what I'm going to be talking about. All right, so let me start over. If we're talking about weight alone, that is a force due to gravity. I'm struggling to write. Okay. A force due to gravity between two objects. And let's just go ahead and identify that mass is a measure of how much matter an object is made of. Mass is essentially a count of the neutrons and protons that make up an object. I mean, electrons too, but their mass is significantly lower. So you're made up of a bunch of elementary particles, and they have mass, and you have a mass equal to their sum, the sum of all their little masses. One of the things that's confusing about this is that the formula to calculate mass is just weight equals mg. You use this in physics all the time, where this is the weight force. It is a force. This is the acceleration due to gravity. Sorry, whoops, my mistake. This is the mass of the object, and this, why did I circle it? And this is the acceleration due to gravity. All right, so when I'm talking about these quantities, W equals mg, it's important to realize that it looks like to me that these are proportional to each other. W is equal to mg. That means if you know the mass, you multiply it by a number, and it gives you the weight. So, for example, if I give you the mass in, let's say, m equals 2 kilograms, find weight in pounds. And, you can look it up, and you can just look up the conversion. You can find that there are 2 kilograms. That, let's say, 1 kilogram is equal to, do I remember this conversion? Yeah, I'm worried, 204 pounds? That seems right. I wish I'd looked this up. You know what? I have the power of the internet. Why don't I use it? Pound to kilogram. Oops. Or rather, I should do it the reverse. Kilogram to pound. 2.204. So glad. Ooh, diamond. Okay, anyway. So shiny. 2.204, so the units cancel. I'm left with 4.408 pounds. The problem with this calculation is that this might feel like a unit conversion, but this is not a unit conversion. I'll talk more about that in a minute, but let's identify this first. This felt like a unit conversion, right? I took my current unit, 2 kilograms, I converted it to pounds, and now I have the answer in a new unit. And here's the problem I have with this. Unit conversions need to be universal. Like 2.204 pounds needs to be equal to 1 kilogram under every circumstance. Certainly, 12 inches is a foot, no matter what. That's just the definition of what those two things are. But 1 kilogram does not have a weight of 2.204 pounds everywhere. Yes, that is the weight on Earth. But the weight on the moon or in deep space or in different places is different because the force due to gravity is different. Additionally, when I say a kilogram, let me write this down real quick. If I say to you that a kilogram, 1 kilogram weighs 2.204 pounds, I really have to say, on Earth. But even that's not the entire picture. Weighs 2.2 pounds, I should say from Earth. Meaning to say, the weight force from the Earth that is exerted on a 1 kilogram object that is on the surface of the Earth is this large. It is 2.204 pounds. There are other weight forces. The sun is currently exerting a weight force on me. And if I had a 1 kilogram object in my hand, the sun is pulling on it too. And the size of that force is not 2.204 pounds. This is specifically the weight force the Earth is exerting on the object. If I move to different places, let me get rid of all this stuff. If I move to different locations, the size of the force changes. If I talk about the force that the sun exerts on the object or the Jupiter exerts on the object, that doesn't just depend on which planet I'm talking about, but where the object is located. This is a complicated thing, and it shouldn't be. Unit conversions should be simple. So this is not a unit conversion. It's kind of like saying this. If you travel let's say you're traveling 50 miles per hour, and you do it for, say, 2 hours. Then you traveled 100 miles, correct? And if we were so used to everyone traveling 50 miles per hour, then we might equate these two things. We might say 2 hours equals 100 miles, which is true at that speed. If you're traveling 50 miles per hour, then you travel 100 miles in 2 hours. And then I could say, okay, well then 3 hours, what's that? Well, 3 hours is 150 miles. And it seems like we're doing a unit conversion. It seems like I'm doing 3 hours times, well, I know that 2 hours is 100 miles, and that's equal to 150 miles. This right here is not a unit conversion because it's not universal. It depended on the speed that we were traveling. And at a different speed, the answer is different. The same thing is true for weight and mass and their relationship with each other. Erase, 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 erase. It depends on where you are and everything else. So it's not a unit conversion. It's a calculation. You are calculating how much a particular mass weighs. Weight to mass is a calculation using W equals mg, not a unit conversion. You can only convert units between two things that are the same dimension. For example, 1 kilogram is, what shall I say? I'll say this, 14.6 kilograms. Okay, doing my best here. 14.6 kilograms is equal to 1 slug. And that's true everywhere universally because these are both masses. Doesn't depend on where you are. 14 kilograms is a slug. Additionally, 4.45 newtons is a pound. And it doesn't matter where you are. This is universally true. These equations are dimensionally homogeneous because this is a mass and this is a mass. This is a force and this is a force. These are unit conversions. Let me write that down. These are unit conversions. All right, so that's the basic thing. If I ask you, let me go ahead and give an example. If I say, find the weight of 3 kilograms in pounds, and you do 3 kilograms times 2.204 pounds per kilogram, I'm curious, what is this quantity? What is it? I can tell you with great certainty that it is the acceleration due to gravity. Because I'm going to calculate a weight, and weight is equal to m times g. Is it evident that this is the acceleration due to gravity? No, not exactly. So let me write it out. 3 kilograms times, let's see, 2.204. A pound is a slug foot per second squared, and a kilogram I'll just leave as it is. I want to convert slugs to kilograms, so I'm going to multiply by 1. There are 14.6 kilograms in one slug. I want to point out I haven't changed anything. I've multiplied by 1. Slug cancels slug, kilogram cancels kilograms, and what I'm left with in the parentheses is 2.204 times 14.6. Wouldn't you know it? That's 32.2, and units are left, feet per second squared. So this quantity, 2.204 pounds per kilogram, is not equal to 1. It is instead equal to 9 point, well, I shouldn't write that first, should I? It is instead equal to 32.2 feet per second squared, which is also equal to 9.81 meters per second squared. This is not 1. It is not a unit conversion. It is just the acceleration due to gravity in a rather sneaky looking package. And true enough, it would be different in different locations, on different planets, with respect to different objects. It would depend on all those things. I've got one last thing to describe, and this is the most important, because even if you buy all that, the question is why? I mean, mass is still proportional to weight, so why do we need a different quantity? Why does this matter? And for that, I need to understand and pull on your intuition for these things. The intuition I want to pull on, I wish I had like a little diagram or a video to go with this, but I don't, and my sketching skills are inadequate for this task, so I'll just describe this to you. If I have you go to this grocery store and put a bunch of things in your cart and try and maneuver your cart around, it will be difficult. Say you're at Costco and you're preparing for, I don't know, some sort of terrible epidemic. Sorry, bad example. And you fill your cart completely with hand sanitizer and chicken bakes. You have a very full cart of items, and as a result, it's hard to move. I mean, when you have a full cart, stopping is hard, starting is hard, turning a corner is hard, everything is hard. And that's because maneuvering a cart, a full cart at Costco, is hard because it has a lot of mass. Not because it is heavy. Oops. I know how to spell heavy. Not because it is heavy. Period. Maneuvering a full cart at Costco is hard because it has a lot of mass, not because it is heavy. And those are different things. The cart, what is hard because the cart is heavy? The cart is hard to lift because it is heavy. That's what's important. The cart is hard to lift because it is heavy. How can I convince you that it is not hard to maneuver because it is heavy? Consider Costco on the moon. If we all take a trip to Moon Costco to buy our groceries for some terrible moon epidemic, if we go to the grocery store on the moon and we fill our cart, a full cart is exactly, well, I'll say exactly, as hard to maneuver. Why? If you fill it with the same junk, if you fill your cart with the same junk, then it's got just as much mass, and it is just as hard to make move. It is just as hard to accelerate it. But it is much easier to lift. Why? It is less heavy, not less massive. You need to understand that weight and mass are different because people associate them with all the same stuff. They assume if it's heavy, then it's hard to maneuver as well as lift. That is not true. Those are independent things. A very large, massive rocket in deep space that has no weight whatsoever is just as hard to make move. It is just as hard to accelerate. Things don't become easier to push when they get lighter. They become easier to lift. So, with that said, I'm going to let this go, and I will, again, see you at a future date. Take a look for example problems for the homework and also for the take-home that is going to be posted this Friday. I will see you later.